So first, I just like to show you that I updated the GitHub repo, which I hope you are all able to find. With the course materials, Anya has volunteered her a scan of her notes for the first part of the course. And then for the homotopy type theory, you now have these links to the videos and the PDFs of what I'm writing. Then here are some external sources that were provided by Yaka, and I here listed a bunch of things, external resources for homotopy type theory. And so maybe I should mention these two, Egbert's notes on Introduction to Homotopy Type Theory, but also a recent one by Martin Escardo, Introduction to Univalent Foundations of Mathematics. It's done in Agda, but don't be scared. It's not programming. It's literal Agda. It's notes. It's actual notes. And there's lots of stuff explaining, natural numbers, empty type, all sorts of things. Everything is done from zero, ground up, and is very precise. So you should find the materials that suit you best. Of course, you could also try just reading the hot book. But I think most beginners find that a bit menacing. So in a combination with the explanations that you hear in the class, together with some of these, I would hope you can cope. Dan Grayson wrote a very good introduction for mathematicians on what this stuff is about. I highly recommend it. It's written for normal mathematicians. So what is the point of this? And then if you want to expand your horizons and think about things like synthetic spaces, a la what Davorin was doing in his PhD, synthetic topology, synthetic this, that. Mike Schulman's these notes are maybe more advanced, but nevertheless I think very interesting. And just for reference, here's the original paper, which connects the homotopy type theory with the Quillen models. What's the argument I was doing the last time to get to the identity type. Okay, so let's go on. No, not this. So today we're going to talk about a thing called H levels. Vladimir Voivodsky made several technical, among other things, several technical contributions to type theory, and one of them is definitely H levels, because they explain a lot of what is going on in type theory, but also they are very natural from a homotopy point of view. So this is what we're going to talk about. So let's just have a very quick review of what we've been doing so far. Review. Okay, so we had the identity type last time. We talked about the identity type. And the way this was written is, there are several ways of writing it. It could be like this, or it could be like this, and this is the one I might stick to. And sometimes I could write this if I get lazy. And the way you think of this is the space of paths from X to Y in some space A. That's the intuition you should have. And what were some basic properties, or the basic structure of this? Okay, so the structure was, first of all, we had the constant paths, which we wrote as REFL because of logic, so write it like this, or maybe just REFL X, where you can guess what the type of X is. This is the constant path at X. So maybe it doesn't hurt to emphasize once again that it's okay for you to think of concrete spaces, and when I say path, you really think of, oh yeah, it's a continuous map from the closed interval to the space. Although at some level this is misleading, because these paths could be more abstract than that. Just like in a general Quillen model, when you speak of the path object, that's not necessarily anything of the form a to the power of something that's like an interval. It need not be like that, and in fact will not be like that in many equivalent models. So also here you have to be careful. So one way to think of this is that if it may sometimes help to think of paths not so much as continuous maps inside the space, but more like morphisms between points. You see, because objects or connections between vertices in a graph, the connections between vertices in a graph are not made of vertices of the graph. And that's my point, is that it could be more like that. Right? If you know what a groupoid is, so a category in which every morphism has an inverse, so a category in which all morphisms are isomorphisms, that's called a groupoid. So that's another example where you can, that one is a very good one because it's the elements of the groupoid are like the points of my space, and the morphisms, the isomorphisms between them are then like paths. So that's another way to think of paths as something other than continuous maps from the closed interval into the space. And so there can be different understandings of what a path means. So another thing that we had was, so we had this raffle, and then we had the path induction. So recall the path induction was, if you want to, so the way this works is, you want an element of a type that says you want to do something for all paths in a space. So you have two arbitrary points x and y, and then you have an arbitrary path between them. And then you want an element, you do want to perform some construction which depends on these. And so now you want something like that. So in general, you would have to consider, take any x, take any y, take any point, and then do whatever you want to do. But the path induction says, no, you don't have to do it like that. It suffices to do it on the diagonals, which means you just take a single point, and then you do it for the constant path. Right? That was the path induction. You reduce. So if I produce an element here, I think we call it something like D, then I will get a general element here, which would then be denoted J blah 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 blah. It was something complicated because you have to record everything that you do. But the thing to remember was that you can pass it to this way. And so then we discussed other properties, and so we discovered that this is like, it behaves kind of like an equivalence relation, right? But I'm putting relation in quotes because, strictly speaking, it wasn't a relation. So let's explain what this means. So first of all, of course, we had, raffle x gives you that x equals x, and last time we were also constructing inv, right? So how did the inverse work? So we had inverse paths. So if I have a path p from x to y, I get a path p to the minus 1 from y to x. And then we had concatenation of paths, which is if I have a path from x to y, and then I have a path q from y to z, then I get a path pq from x to z. And you can read this as operations on paths, but you can also read them as logical statements saying that equality or path space is reflexive, symmetric, and transitive. Now, why am I putting relation in quotes? Because these are all really just constructions on spaces. And when you get to the properties, right, then you say such that, and then you prove something like this. For every, so suppose I have, so for every x, y, for every x, y in A, and the path P from x to y, we have, for instance, that p times p to the minus 1 is REFL, let me get this right, it's probably, so this one ends at y, so it's going to be y, REFL y, yes? Now, I'm being careful because this thing here, right, is not just like ordinary equality. This also is a path space. What instead of saying that when we say that p to the minus 1 is the inverse of p, we don't really say that when you concatenate them, you get exactly REFL. What we're saying is that there is a path from here to here. So this is a two-dimensional path. So where is this happening? This is taking place in paths from y to y. Yeah, it's taking place here. It's a higher dimensional path. It's a path between paths. It's like a homotopy from y to y. And
the first path is from x to x.
You're saying that what?
It should be REFL x.
Oh, should be REFL x?
Yeah.
Okay. How about now? It was easier to fix. Okay. So it's happening. It's happening from what? No. I have undo. Let's be careful. So let's look at this one. Okay. PQ means, let's draw a picture. This is not composition of functions. This is concatenation of paths, which I'm writing like this: x, y, z. P goes from x to y, q goes from y to z, and then the concatenation goes here. So this is PQ. Okay. So I think P ends in x. So this thing goes from y to y. No.
No, P ends from x to x. P goes from x to y.
So, oh, I see. Okay, thank you. Yes. Okay. This is why I want to prove. Okay, so now the point is that this is now saying something about how there exists a map which takes this input and gives you a homotopy like this, and this map is continuous. And then this is the space, this is the loop space at y, so it could be very complicated, and this could have an interesting structure. So this is not just some statement about how things happen to be true. This is a statement that says that certain maps are possible. And there is a lot of structure to these maps. That's why I don't want to call this a relation, because it's really more like a structure. And we're going to make this much more precise today, and then the next lecture we will make it precise what the difference between a property and a structure is, and then we'll see why we don't want to call this a relation. Okay, so then there were other laws, so let me just jot them down. So the other one was that p times p to the minus 1 is REFL, and then there was associativity, PQR is PQR, and they are all of this form that there are certain, it's possible to have certain paths in certain spaces. And what am I missing? P and REFL gives you P, gives you REFL and P, and you can figure out these exact subscripts by yourself, like there are missing subscripts here. Okay, so this kind of structure is groupoid-like, right, as I was explaining the other day. Okay, then we also had that we can map paths along functions. So mapping paths, which was, suppose you have f from a to b, and then you have a path p from x to y in a, then we can get the map f acting on p. I'll write it like this: f of p. You can just write it f of p, which is going to go from f of x to f of y, and it happens in b. And this was functorial in p, right? When people say functorial, what they mean is preserves identity in composition. So this means that f of REFL of x is going to be REFL. This was in A, this is in B of f of x, and f of PQ is going to be FP FQ. And you can prove all of these are exercises in using path induction. Okay? There was also the idea, this is the idea we started with, was that dependent types are fibrations, and then we had the lifting property for paths, but since I'm not going to use that today, I'm not going to dwell on that. So let's get to something more, let's start doing something else. Okay, so to start talking about the H level, let me start with the lowest level, which is called the contractibility, so contractable spaces. First of all, what is the classical definition of a contractible space? A space is contractible if the identity map, there is a homotopy from the identity map to a constant map. But first of all, to have a constant map, your space needs to be inhabited. It has to have an element. So you pick some element, right, like X, and then you say the constant map on X is homotopic to the identity map. Or to say it another way, the identity map is null homotopic. That's the definition of contractibility. So how do we, so what is an example of a non-contractible, like what is an example of a contractible space? Point, a real line, a closed ball, open ball, those are all contractible. Non-contractible, circle, sphere, yeah, sufficiently interesting manifolds, yes. Okay, so let's try to define that in homotopy type theory, and this is the definition. Now this is all Vladimir Vygotsky originally. So definition, we're going to say that a space or a type A is contractible when, so now I'm going to write down a type. And when you say, if I say when a type, that, so somebody says when a type, that means the type has a point, okay? You will see later why that means, but let's be explicit about this now. When there is a point in, okay, the space. Now what will be the space? So let's see, we have to say that we need a point. And now we're not going to say the identity is null homotopic because we don't actually, we're not too sure how to say that. So we're going to say this: there is a point such that every other point, oh, sorry, xa, pi, ya, xay. Or let's define this as is contour. So if you ever read any formalization, it's going to say is contour means by definition this thing here. Okay, and so we don't say there is, see, we don't really like to say there is a point in, because we don't want to do logic. This is logic to say there is a point in. What you say is you just give a type, and then to establish contractibility of A means to give a point in this type. Okay, there's no there is a point. You just give the point. Okay, so
it's not the same thing. People said that there is a path connecting.
Sorry?
It means that the space is path connected.
Yeah, okay, so yes, exactly. So this is exactly the thing that I want to discuss next. This definition, at the face of it, when you read it, it says that every point is connected to X. Okay? That's what it says. There is a point X such that every point Y is connected to X. Now, if I did this in classical topology, what kind of a space is it if it has a point and every point is path connected to it? What kind of a space is that? That's path connected. Well, okay, that's a non-empty, right? It's a non-empty space, and it's path connected. That's precisely going to be path connectedness. Yeah? Okay, so it looks like I got the wrong definition. And because this should be maybe path connectedness, but no, I'm saying it's contractibility. And the reason why it's contractibility is that you need to remember that the way you read this pi here is as a continuous section, right? So when you think about the pi says that there's a continuous section. So the path from x to y will vary continuously with respect to y. So the classical reading, traditional reading of this definition is there is a point x in A and a continuous map well, what kind of a map is it? P, which goes from A to the 0, 1. So it goes from, for each point y, it gives me a path such that P of y at 0 is x and P of y at 1 is y. That's what this definition says. This is the correct reading. But under this reading exercise, this is 1 is classically the same thing as A is contractible. Because this P here is more or less the homotopy showing that the you see, I just transpose it, I will get precisely what I want. See? Yeah? Okay? So that's why this is contractibility. So the question now is, okay, if this is contractibility, but how are we going to get path connectedness? Because now it's, okay, we got the contractibility, we definitely want path connectedness as well at some point. So that's now becoming a dilemma. Okay? So let's have an example. We don't really have very many examples yet, so we're going to do a silly example. The unit type is contractible. Remember that the unit type was a type which just had one point called star. Okay? So how do you prove this? Well, you don't prove it, you construct it. This is not logic. I need an element of this type. So I stare at this and I say, okay, so construction. What is an element of this type? This is a sigma type. Because it's a sigma type, its elements are pairs. So it needs to be an element of 1. So this needs to be a pair. Okay, so the first component needs to be an element of 1. There isn't much choice there. We're going to take the star. And the second one needs to be a function of this type, where x is now star and a is 1. So here, I'm now looking for a function pi y1 star 1y, like this. Okay? How do I get such a function? Well, I need to remember what my definition, when you define the unit type, you need to know what its property is. And its property was that in order to define a function out of 1, you just need to say where the star goes. Okay? Yes? So to get a function here, you would say, so this is a function f, okay? And f is defined by f of star equals, so I just need to, define what f does to star. That's sufficient, because that was the induction principle for the unit type. Okay, where does this have to go? Here, I'm looking for something that is in star equals 1 star, but that's easy, that's a REFL. Okay, so this was an exercise, how you could do this. Okay, so that's contractibility. And now the next level, the next step is called H levels, or homotopy levels. And there is a or truncation levels. there is a very unfortunate story here. These are levels which go up by natural numbers. There is h level 0, h level 1, h level 2, and this is how Vladimir reasonably started numbering them. And then we wrote the hot book, and for some reason a committee decided that the correct way to number them is to start with -2. So now there is permanent and never-ending confusion in the homotopy type theory, because depending on where you come from or who we were taught by, you might be off by 2, okay, with respect to your speaker. So which one should we use?
You can start with -1.
Sorry? Well, we should start with -1 to be in the middle, take the middle ground. Yeah. Okay. Now, the reason for 0, 1, 2, 3 is because that's how we count. And the reason for -2, -1, 0 is because the level, this level here, this one, which is 2 in the other one, right, corresponds to components for the path-connected components. And 1, level 1 here corresponds to the first homotopy, to the fundamental group. And level 2 corresponds to the second homotopy group, and so on. And so if you use H levels, then all your fundamental groups are off by 2 in their numbering. And that's why it was decided that we shift by -2 to -2 so that we get back to the normal counting of dimensions. Okay? So that's why it happened. And we are going to use the truncation levels, but you should be aware that this is really, really bad. Somebody will talk about H levels, but they mean the truncation levels. Okay? So it's going to be really horrible. So whenever you speak to somebody, you have to ask them, which is the lowest level? And then they say, if they say 0, then they're like the original thing. And if they say -2, then they're like the alternative thing. We're going to use the alternative thing because it's in the hot book. And because it corresponds with dimensions in homotopy theory. And after all, this course is all about homotopy theory. So let's stick with that numbering. Okay, so I hope I don't make any mistakes now. Okay, so the truncation levels now go like this. Okay, so first of all, we define. So we're going to define what it means for something to be an n-type. Okay, for n goes from -2, -1, 0. By the way, you can imagine it's lots of fun when you formalize this in a proof assistant when you have to start counting with -2. It's just excellent. Okay. So I think we define in the hot library, we define custom-made data type of numbers from -2 onwards, just so that we deal with this stupid issue. There we go. So n-type. Okay. So first of all, what is a -2 type? A -2 type. A is a -2 type. That's the same as is contractible. And then, what is an n+1 type? A is an n+1 type if its path spaces are n-types. So for every x and y in A, the path space from x to y is an n-type. That's a definition by induction on natural numbers starting with -2. Okay? Okay, so that's a definition now, but why is this definition any good? We need to let's look at these levels and discover what they are. What are they saying? First of all, -2 means is contractible. Okay, so we already have that. So let's look at the -1 types. I got my title wrong, didn't I? H levels. Yeah, see, now we have to change the... This is just so horrible. Okay, so what about -1 types? Let's see what these are. let's write down explicitly what it means. Okay, so what I want to say is A is a -1 type when we can produce a point in pi x, y, a is contour x, a, y. I just plugged in the definition for -1 and unrolled it. So now let's show that this type, let's call this type now, I don't know, P, okay, that P, that we have maps, P implies, so there is a map from here to, for all x, y in A, x, a, y, and backwards. Okay, so why would I do that? So A is a minus type when it has a point, when there is a point in P. But if I have maps going back and forth between two types, then this one has a point if and only if that one has a point, which means that I can reason about this. If I want to establish that A is a -1 type, instead of doing this, I can do that. I can find a point in here, and then I transfer it back, and I know that they are co-inhabited. Okay, so let's see. Let's go in this direction. So we want an F and we want a G. Okay, so first of all, let's say we want this map. Actually, I'm not going to call them anymore. So I'm just going to do this like this. Okay, so suppose we have F. So P is a function space. Suppose we have F in P. Okay, we want, what do we want? We want a point in, and you should observe how I construct these things, because that's how you do type theory then, also with the proof assistant. Okay, we want a point in here. So that's a point in here is just a map. Okay, so let's call this map G. What is this G going to do? Well, G it will take an X and a Y. So G is going to take an X and a Y in A, and now I need to produce a map from X to Y. Where will I get a map from X to Y? Well, obviously I have to use F. So let me draw a little picture here. So here's my X, here's my Y. I want a path from X to Y. What does this F do? Well, F is an element of P, so it takes 2 points. So how about if I calculate F of XY? F of XY is an element in here. So I have that fxy is contour x equals y. Okay, I apologize, this is a little too unreadable. Let's see, we have fxy is contour of xay. Okay, but is contour is a sum. Where is it? It's a sum. Okay, so its first component is a point in A, and its second component is a function. So let's write down what this is. Okay, so pi1 of fxy is a point in A. Here it is. What is pi2? Pi2 fxy, it's a map which takes any z in A and gives you a point which goes from pi1 fxy to z. That's what it is. Okay? So now this means, look, pi2 fxy, this is a function. I give it z, it'll give me a map from this point to z. So if I give it y, it'll give me a map from here to y. That would be the map. This is the map pi2 fxy applied to y. And if I give it x, if I apply this map to x, so I plug in x for z, I will get a map from this point to x. So I can also get a path which is pi2 fxy x. So now I have, but now I can get a path from x to y. So this path would be, let's try to write it down here. So this path would be, it has to go from x to y, so it's this path to the -1, pi2 fxyx to the minus 1 concatenated with pi to fxyy. So you can draw pictures, or you can write down terms, and that's what it works. Okay? So now, which means now we know how to go from P to this space. Given F, I produced a G here. Now suppose the other way, suppose I have G in this space by xya, xay, such, and now we want F in P. Okay, but let's write down what is this P. Okay, P is this pi xy is contour thing. Pi xya. Let me write down what is contour is contour. Is contour will say here, I will plug it in. So there exists a point, there exists a path from x to y such that for every other path from x to y, p equals q. This is what we want. So how will this f work? Well, now I already know. F, it'll take x and the y. I just follow my nose here. Okay. I mean, I can write it like this. I could write f equals lambda xy, but this is also okay. I just need to, if you want to be super exact, lambda xy in A. Now I need an element here, so I need to give a path from x to y, and then I need to give a map like that. Okay, so where am I going to get a path from x to y? Well, clearly by using G, but G is precisely, Gxy is precisely a path from x to y, so this is just Gxy, that's a path from x to y. Okay, and now I need to say, if I have any other path, Q, which goes from x to y, how am I going to show that P equals Q? Any ideas? Did I do this right? I hope I did it right. Yeah, I think I did it right. Okay, so this I think I'm going to give you as homework, because I don't want to get into it now because I'm looking at the time and I'm just like, oh my god. Okay, so conclusion, this -1 type is the same thing as this thing here, at least co-inhabited. We can later prove that these two maps are actually equivalences and P is actually equivalent to this, but we don't know that at this point. So -1 type -1 type A, it'll turn out that this is equivalent to pi xya xay, and let me call this is prop A. And now let's read this statement a little more classically. What is classically, if you think this, what this says? If you think of A as a set, it says that A has all elements of A are equal, would be the set theoretic reading. So that's just a fancy way of saying that A has at most one element. Actually, that is not a fancy way. That is the basic way of saying that A has at most one element. If you say at most one element by using the number 1, that's a fancy way of saying that it has at most one element, because then you have to know what 1 is. But this way you don't have to know what 1, the number 1 is. So, a little more topologically speaking, what is this saying? This is saying that there is a continuous selection of maps between x and y, continuous in x and y. That's not, I mean, you know, like, that's interesting. For instance, you couldn't do this with a circle. So it's saying something. And what, but also notice that A could be empty. Nothing forces A to have a point. So this is something like A is empty, but as soon as it has a point, it'll actually be contractible. So if we cheat a little bit and think classically, okay, so these are the empty spaces and the contractible spaces, something like that. But those correspond to truth values, because in logic and set theory, so you can always represent propositions or truth values, propositions as in logical statements, right? Or truth values. Can be represented as spaces. Okay? So here would be a bad way to do it. You say true is represented by the space 1 and false is represented by the empty space. Okay, here's a better way. The problem with this is that I only, you know, this works if you believe in excluded middle, where everything is either true or false. That is to say, everything is continuously either true or false, because everything is continuous. So we just want to say the same thing without considering two cases. And so the way you say this is, so classically as a set, so classically you would say something like this. You would say those elements of the singleton star, those elements of the singleton star, so for which P holds. Okay. What does this do? Well, you see, if P is true, then this P does not depend on you. It's a bit of a silly definition, but it works. So if P is true, you're just going to get 1. So here you could actually would be a little more clear if I write here 1. Okay. So classically, just a set, you would say take all elements of 1 such that P. So if P is true, you will get 1, and if P is false, you won't get anything. You'll get the empty set, 0. So this is the same thing, but without using any implicitly using any kind of distinction between true and false. So, in other words, see 1, 0, these are all spaces with at most one point. So a space or a set with at most one point is like a truth value, because if there is a point in it, then it represents true, and if there isn't a point in it, then it represents false. And if we're in some weird intuitionistic thing with in-between possible strange truth values, then a space with at most one point represents a truth value, and it's as true as it is inhabited, right? It's as true as there might be degrees to which it has a point, and it's true to the degree to which it has a point. So that's why this is going to work in a general way, and so that's why we call these things propositions. So we therefore call the -1 types propositions. Because they behave like truth values. They are not about structure anymore. A space which is a proposition. So this is a space, it could be empty, but if it isn't empty, it's contractible. a space like that doesn't have any interesting structure. It doesn't have any, there's nothing you can say about its points that's interesting. The only thing that's interesting about it is whether it has a point. After that, you don't care. So whether it has a point is how you represent the truth, or a level of truth. And so that's why we're going to call them propositions. Is this a good point to break? Yes, because we're now next going to look at the H level 0, but let's do that after the break. So let's have a short break, 10 minutes. Like this, what's standing here. The homework, the exam would consist of some reasonable collection of a body of exercises that fit together somehow. You know, it wouldn't be totally random selection of stuff. Like it will be some small corner of basic homotopy type theory. Okay. That was H level -1. So let's have a look at H level 0. Okay, so H level, homotopy level 0. So 0 types. Truncation level 0. Okay, so truncation level 0. This name will be clear shortly when we introduce truncations as operations. Okay, so this one comes down to what? Well, this one is for all, let me write it out, what it comes down to. For all x, y in A, now we have to go on. For all x, y in A, the identity type is a proposition. So now I need to write down that the identity type is a proposition. So the identity type from x to y, it is a proposition, is, I'm using the previous one, for all. So I'm now implicitly using the fact that this is actually equivalent to the original definition, but that's how we do it so that we can understand what's going on. If I have any two paths p, q from x to y, they're equal. This is what it is. This is truncation level 0. What does this say? For any 2 points, the path space is a proposition. So, okay, so it could definitely happen that I take x and y, and there are no paths between them. And so then the space of paths from x to y will be empty, and so that's okay. So one possibility is that x and y don't have any paths. Another possibility is that there is a path from x to y. But as soon as there is a path from x to y, all paths from x to y are equal in a canonical way, so in this continuous way. So the two possibilities that we have seen so far is the paths from x to y could be empty, or they could be contractible. Yes. Well, that means that my space is very disconnected because it doesn't have any interesting paths, so to speak. So it's just a bunch of connected components. And so this one is called, these things are called sets, okay? And so we define, so such a type has no interesting paths. We call them sets. We call it a set. So this is a set. It's a little bit misleading because you might think that it's a discrete space. So rather than thinking of a discrete space, think something like zero-dimensional or totally disconnected. So it's just dust. Okay, so it's a bit like dust. It's not quite right because some of the components could be contractible. So all its path components are okay. So that's maybe the way to say it. All its paths are all of its path components are contractible. All of its path components can't write components. Components are contractible. That would be a classical way of understanding what's going on. So we define is set A means that it's a zero type. Okay, we can go on. So what would one types be? Well, one types, these are going to be things whose identity types are sets. Okay, so you have a space, and then if you look at the path space between any 2 points, you see a set. And that's going to be a groupoid. So we call them groupoids. Why do we call them groupoids? So the traditional definition of groupoid, again, is a category in which every morphism is an isomorphism. In particular, because it's defined to be a category, there are no two cells. It's not a two category. It's a category. It's not a two category, which means no paths between morphisms, no natural transformations between morphisms, no homotopies between paths. And that's the meaning of the path space is always a set. There aren't any interesting homotopies. There are interesting paths, but there aren't any interesting homotopies between paths. That's what you can think. That's how you could think of a groupoid. And this goes on, and then people run out of names. Then they call them two groupoids and things like that. But it's just better to start calling them n types at that point. Okay? So now let's go back and consider, is this number 3 now? Number 3? No, number 4, probably. If I manage to number things correctly, this one should be 4. So we have now identified certain nice properties of types, that certain types are propositions, certain types are sets, certain types are groupoids. By the way, careful. You could ask, does every type have an n level? So maybe just as a fact, I should explain. So maybe explain also some observations. So this goes on. So first of all, if you have if something is an n type, it turns out, and this is something that you need to prove, then it's also an n+1 type. So once you kill, so another thing to think about it is like this. An n type doesn't have any interesting homotopies at level n. Right? So this is something we would need to prove, but this turns out to be the case. So you always have this direction. And also the other thing, so some observations. It need not be the case, not every type has a level. I.e., you could ask, given some type A, do I always have n type A for some A, n? Does there always have to be a level at which it stops? And this is in general, the answer is no. And we are going to if you want an example of such a type, is example is a two-dimensional sphere. Well, now you need to know something about this. So a two-dimensional sphere, one way to see this, does a two-dimensional sphere have interesting homotopies at every level? It does, right? Yeah, at infinitely many levels. And so this is one reason to expect that this would be the case. There are also important possible additional axioms that one could take. For instance, a very common axiom to take is that you say all types are zero types. In which case you're essentially limiting yourself to just sets. You're saying, I'm just going to observe sets, but we're not going to do that. So that's an important principle. It goes under different names, such as the uniqueness of identities principle, because the way you can read that, you see, the way you can read this statement here is all paths are equal. It says all paths are equal in as much as this makes sense. If I have two paths that can be compared, they are equal. If they're all parallel paths are equal. And so that's why people sometimes call this principle uniqueness of identity proofs, because paths are proofs of identity. And so paths, if there is one from X to Y, it's unique because all of the others are equal to it. So that's UIP. You will sometimes hear people say UIP. Maybe write this here. This is UIP. When they say UIP, they mean the statement that everything is a zero, that everything is a set. Okay, so now we have this. We have a universe, and inside the universe, we have n types, sitting n types. So let me define now. Let me write it with a capital T. N type, like this, with a capital type. Sure.
You didn't really explain how a sphere is a type of uniqueness.
Okay. Next time we're going to explain how to make a sphere. We don't know that yet. But we will not explain why it doesn't have an n level, why it's not truncated. Because to explain that is going to be, see, if I manage to explain that, I will have explained, more or less, that in every model of homotopy type theory, when you make a two-dimensional sphere, all of its higher homotopies are non-trivial. So that is going to be at least as difficult as proving classically that the two-dimensional sphere has infinitely many interesting higher homotopy groups. And that is not easy. So you shouldn't expect, if I can do that in 5 minutes, that would be really, really good. But I can't do it. That would be impressive. But we can do it. It's just not in 5 minutes. Okay, so how would you define the type of all n types? Well, you would define these are all the types in the universe such that this one, notice now the lowercase type, n type A. Yeah. So an n type, an element of this is a type A plus evidence that it's an n type. So an element of a some type. And so now n type is sitting inside U, right? So n type is sitting inside U because I just take the first projection here. Every n type is a type. You just forget the second component. So the question, and this is actually an embedding of a sort. So the question is, can we go back? Is there a way to take a type and force it to be an n type? That's what I want to consider. This is a common question. For instance, let me give you one example. Commutative groups sit inside groups. Right? So commutative groups are a special case of groups. And so it can ask, is there a way to take a group and force it to become a commutative group? Can I take a group and make a new group out of it such that the new group is commutative? The answer is obviously yes, just take the integers. Okay? But that's a really bad way to force a commutative group, to make a group into a commutative one, because it's not interesting. It doesn't have any good properties. What we want is, you want the best way to make a commutative group out of an arbitrary one. How do you say the best? And so here is where category theory comes in. And you say, well, the best means either left or right adjoint to this functor. There is an inclusion of commutative groups into groups. And you can ask, does it have a left or a right adjoint? So the left adjoint will be the most economic way of making. One way to think of it is you want to make a group commutative by destroying it, so to speak, as little as possible. And the right adjoint is you want to do it in a more chaotic way. So these are not precise analogies. They work well in some cases, in some other cases they don't work so well. So the economic way maybe is easier to understand if we look at the different. Let me look at another situation. Every group is a set because it's a set of elements. So I can ask, given a set, is there a best way to make a group out of it? Yeah. And so now the left adjoint will be, yes, it's the most economic way to make a group, which means I take my elements of the set, and then I want to start I want to put the structure of the group by adding as little as possible. And that would be the left adjoint. Yes? The right adjoint is different. I don't have a good description of right adjoint. What does the right adjoint do? Do you have a good one?
Something like a closure. The right is something like the interior.
Yeah, okay, so that's a good point that Davorin makes. The left adjoint is like a closure or a completion, like a completion of a metric space. The right adjoint is typically like the interior or the good part of, right? You have some good part of things. So, and you take that. Okay, so is there a best way to turn any type into an n type? And such, okay, so it turns out with the constructions that we're going to, the higher inductive types that we're going to consider next time, there is a way to do this. But it's just like with free groups, okay? You can say what a free group is. A free group is the best way to make a group out of a set. Or yeah? You can just postulate that they exist without knowing precisely how to make them. Or you might have an abstract reason for knowing that they must be around, but you don't know how to concretely to make them. It doesn't matter. They're going to have a universal property which already tells you everything about them that there is to know. So this is what we're going to do. I'm going to postulate, I'm going to say, there are these truncations, and then we're going to explore them. And then the next time we're going to see how to actually make truncations with your bare hands using some other technique. So speaking very, so if I say an n truncation is the left adjoint to the inclusion of n type to U, then I'm done. So if I'm at a category theory conference, I just say, yeah, it's just the reflection of n types into U, because this is an inclusion, and then a left adjoint to an inclusion is usually called a reflection. So, but that would be it. But let's be explicit, okay? So definition. The n truncation of a type A is given by, and now I'm going to write down in type theory a universal property which says left adjoint. And so this you read it, I think the best way to read it is you read it as if I'm doing some sort of completion. If you're thinking it's like completing a space, okay? So then it'll make sense. I think that would be a good reading. So Davorin suggested to me to use this example, to use completion over lunch. So let's see if we can go. It's given by. So first of all, we have a new type, which we write like this, which is a type. Okay? And then for every, so there is a map, which we write like this, which goes from A to the truncation, the n truncation. Okay. So, i.e., if little a has type A, then this absolute value n has type truncated an, like that. And now, so you think of this as the completion, you think of this as the inclusion into the completion, yes? Oh, there's a second reading which would also help. Think of this as some sort of quotient of A, and so this is the map from the set A to the quotient. That's another way to think of it. Okay, and now something else. For every n-type B and a map F from A to B, I need to give you the dependent version of this. So let me give you, actually let's be exact, let me give you a dependent version of this. Okay, sorry, it's going to simplify, but I think it's better not to simplify. Okay, so given so we don't have a fixed B, we have a dependent B, given B, which goes from A to n types. So I have a family of types indexed by A, but they're all n types. Okay? And so now what I want is I want to be able to factor this through A. So let me draw a picture. I have A, and here I have n type, and I have B, and I have the truncation like that, and there is this map, right? This is like blank, you write it here. Okay, I want to be able to map it. I want to be able to do this. Okay, there is something here. I'll call it B prime. Such that this commutes. So this is the sort of thing you would want to say. So let's maybe look at the non-dependent version of this, because this would be the type to that. So the non-dependent version would say, if I have A, and now I'm going to have a fixed, I'm totally confusing myself and everybody else. I apologize. I may have to delete this from the video, because otherwise the entire planet will know that I don't know any type theory. So let's see, oops. Let me give you the non-dependent version. I apologize for this. Given, we go again, given F from A to B, where B is an n-type, we have F bar. So the dependent version would be this, but then this F would have to be a section. So it's the previous picture with a section. Let's just stay with this. It'll be easy to understand. F goes from A to B, where B is an n-type. We have F, which now goes from this one to B, such that, so let me draw a picture. A, B, no, A, like this, A, N, N, B, F, F. So such that this commutes. What do I mean by that? Such that for all x in A, f of x equals in B, f bar of the truncated x, like that. The dependent version I was trying to get at would take this B to be dependent on A, and then this F would be a section of the pi, and then this one would be a section of the pi. Okay, but let's stay with this because this one now shows this is exactly how you write down universal properties. For instance, let's see, let's say something like completion. Okay, so you have a metric space, you include it into the complete metric space. Now, if you have a map from A to a complete metric space B, I'm skipping over some questions of exactly what kind of maps they are. So you need to be careful what maps there are here. Yeah, it's better to have them uniformly continuous. So we do this for uniformly continuous maps. So A is a metric space. This is its completion. This is the inclusion. If I have a map A, which is uniformly continuous into some complete metric space B, then it will factor uniquely. And so this is what, so that's why this is like, it's like that. Okay, it's a property of a left adjoint. The point of this is that we get an operation which allows us to kill higher homotopies at any level we want. So next time we will see that we can actually make those using some gluing techniques. Okay, so they're really gluing techniques where you glue in a lot of, you throw in lots of paths, you kill everything above, right? Or you throw in lots and lots of two-dimensional paths, you do things like that. But for now, let's look at the concrete examples of truncations. Okay, so the most important one for is, well, the most important one for a logician is propositional truncation. So let's have a look. Propositional. Okay, so here NB actually need a dependent version. Where you have f by xa bx. Okay, so just this was oversimplified. So propositional truncation. What does this do? Well, that's just bar a minus 1. So how do you view this? What does this one do? Okay, so this one is, it just glues all the points together. So classically, this one would be, so traditionally, corresponds to A quotiented by the equivalence relation where x is equivalent to y for all x and y. So if I told you that I'm making a quotient by the trivial, so there are two trivial equivalence relations, the identity and the full relation, which identifies everything.
I'm so sorry,
Yeah.
but here should start tutorial part of the German.
No, I'm really hoping you're wrong because we still have 15 minutes of lectures.
Okay. I'm
So maybe
sorry,
it's somewhere. Maybe it's somewhere else. Are you teaching or what? Who's
Yes,
teaching?
I'm teaching.
Okay.
Or should I?
I don't know. So can you maybe Anya? Can you help
Sorry
out?
to bother.
She's going to look up on the schedule what's going on, and okay, we'll tell you. Okay. So traditionally, this corresponds to just bunching everything together. So what happens? Well, first of all, if you have the empty space and you do this, you will just get empty space. Let me write equivalent, not equal. Okay. If you have, if A has a point, so if we have a point A in A, then when we do this, it's going to be contractible. Because in essence, what's going to happen is you have your space A, it may have had several components, then you have an A, you just put in lots of paths everywhere until you're blue in the face. You connect everything. you make a complete mess out of it. What you get is a contractible space. So that's what was going on? Wrong.
They just wanted to start early.
They wanted to start early.
Yeah.
Yeah, okay, they're not going to start early. So, this is propositional truncation. For an inhabited space, a space with a point, it will give you a contractible space. For the empty space, it will give you the empty space. Why is this good? What do we do with this? Okay, so this can be used, propositional truncation can be used to force any type A to become a proposition. What is this proposition? If I have a type A and then I truncate it, what is the proposition? It's the proposition that A contains a point, but importantly, without giving you a point. Yes, so this is super important now. And this we can use, nope. And this we can use to encode, so here's an application, encoding of logic into type, encoding of logic into type theory. We started type theory as a theory of constructions, of spaces and points. And so the question is, how are we going to recover logic? And here's how we're going to recover logic. We're just going to think of, we're going to follow the idea which I mentioned earlier, which is that we think of spaces with at most one point or as propositions. So let's do that and ask, and then having a point means being true. So truth is just going to be the one point space. Falsehood is going to be the empty space. And now, given P and Q, which are propositions, so they need to be -1 types, how do I get the corresponding logical connectives? So then you need to, so now you need to actually prove that these constructions will give me -1 types. So P and Q is just going to be P Cartesian Q. If you think about it, you want this to be inhabited if both are inhabited. So you take the Cartesian product. Yes? Okay, so then what is implication? I want to have a map from P to Q in case, well, in case Q is as inhabited as P is the way to say it. And so that's just the function space. And then once I have that, I can get negation, because negation is logically equivalent to saying P is as, what is, P is as inhabited as the empty space. Which one? This means, which way does it go? Q is as inhabited as P, right? Because if P is inhabited, then Q is. So to say not P is to say that Q is as inhabited as 0. And then, importantly, P or Q. Okay, so here I don't say P plus Q, because if I say P plus Q, I'm not going to get a proposition. If this has a point and this has a point, this guy is going to have 2 points. So I truncate. And then given, let's do first order logic as well, given P from A to -1 types, so this is now a predicate. If I have a dependent family like that, then I can define for all x in A, P of x is just pi. But then exists if I said that this is, so you need now a theorem saying there's some trickiness involved in saying, okay, so why is this a -1 type? This is a product of types, each of which has at most 1 point. And you want to know that this space has at most 1 point. So, I mean, again, this is something you need to prove. How about this one? Well, now if you would say, okay, so how do I show that something exists? Well, I give a witness and a proof that it holds. But again, this is not going to be a proposition, because suppose this is always true. Well, then this guy here has as many points as A. So I truncate. And this way I get exactly the rules of logic become valid. and I get what is known as intuitionistic logic. Because it doesn't have excluded middle. But, as is known, can also assume, if we want to, not that we want to, but if we want to, lem, law of excluded middle, which would state this: for all p minus 1 type, p or not p. We know it's consistent. Nothing breaks. All univalence, everything still works. So it's okay to have lem if you want to. Maybe I can comment. So what the heck was going on here? Okay, so spaces with at most one point, we use them for logic. The constructions are as they are written here. A lot of them agree with known constructions like conjunction is product. This goes under the name Curry-Howard isomorphism. The traditional Curry-Howard isomorphism is without these truncations. So you just ignore the truncations, and then you get what was known for a long time. This is known as Curry-Howard isomorphism. But let me comment here is something interesting from the point of view of foundations of mathematics. The difference between plus and or, and between sigma and exists. To say p plus q, what does it mean to have an element in here? So if I have an element in here, t will tell us which one holds. Why? Because every element here, because it is of the form in left of something or in right of something. Yeah? And so if I say p plus q, what I mean is the concrete kind of disjunction where not only am I claiming that P or Q holds, I'm claiming we also know which it is given, which of the two is meant. Whereas if I say T is in P plus Q like that, so that would be P or Q now, right? Like that. Then T does not tell us which one holds. Why is that? Well, T has form truncated, right? It's going to be truncated in left something. And it could also have or truncated in right something. But suppose you find out that T has this form. That doesn't tell you that T is proving something from P, because this form equals the other form. T is also equal to, every truncated in left is equal to every truncated in right, because by force they were made equal. And so if you tell me that T equals truncated in left, that doesn't say anything, because they're all equal. The information has been lost. It's hidden now. You don't know. So this is concrete disjunction, and this is abstract disjunction, where you don't know which one holds. And this is something that is very much present in mathematical practice. Mathematicians, if you observe how mathematicians work, they very much use this notion. And similarly, for exists, if I say sigma xa p of x, this means I'm giving you a concrete existence, I would call it. I need good names for these. Concrete existence, where we actually have a witness. It's going to be the first component. If I have t here, then p1 of t gives me something in A. But if I have t in the truncated one, then, well, this t is of the form, t has the form truncated pair, but that doesn't mean anything because it's equal to all other truncated pairs, and so I don't have a witness. So this one is abstract existence. Here I think is an important for a logician, because we have, well, some small number of logicians in this room. For a logician, this should be interesting, because it's capturing something that first-order logic, even intuitionistic first-order logic, does not capture. It's the difference between concrete and abstract existence and concrete and abstract disjunction. Whether you have the information on what it is that exists, or whether you don't have the information on what it is that exists. How did this arise? I think the primary reason for why this arises is that we did not, from the beginning, we did not insist that logic needs to be separated from construction, like it is in first-order logic and set theory, where you, or even in topos logic. In topos logic, like you do internal language of a topos, it's the same thing. You very much separate logic part from the construction part, and here it's all mixed up. And so because it's all mixed up, it allows us a more complicated forms of expression.
The language of a topos is a type theory.
The language of a topos is a kind of type theory, but it's a simple type theory that is, you can also interpret it as a kind of bounded set theory if you want to. And there are actually formal ways of making this statement true. Out of every topos, you can make a certain kind of set theory. Okay, what is this? Are there some nice applications of this? Yes. So let me give you some nice applications. By inserting these truncations, we get to say things in the correct ways, or we get to say different things. Let me show you an example. Example. Suppose you have f from A to B. Now compare the following. For every x in A, for every y in B, concretely there exists x in A such that f of x equals y. Versus for every y in B, oh, let me write it, okay, like this. Truncate x in A, f of x equals by minus 1. So this one would be the same as saying, in terms of logic, this is for every y in B, there exists an x in A such that f of x equals by. Okay? So what do these say? This one has a section, because this one says f is split epi, i.e. has a right inverse. Homework. Why does it have a right inverse? So if you give yourself an element of this type, then you can cook up a right inverse. Yes? Whereas this is properly what we mean by f is surjective. Yeah. Another example, how do you write down the image? So this is maybe the last example, and then we can kind of finish. Okay, so another one is, how do you write the image of f? The image of f, you say, what is this? You say, it's the set of all y's. So you take the y's in B, the type of y's in B, such that what? Well, now if I say, now I need to truncate. Now I need to say, there exists an x in A such that f of x equals to y. Because if I put sigma here, would be wrong. Because then image of f becomes always isomorphic to A. That's going to be another exercise. So if you put in the sigma, you get a silly thing. You can show that what you got is always the same as A. But if you put in exists, you get exactly what you want, which is the image. Okay? I see that there are lots of nervous people there. So let me just finish with a very small section. What about one truncation? Oh, sorry, zero truncation. Zero truncation. So what is this? Okay. This says now we're not gluing everything together. Now what we're doing is whenever we have when we take x and y and we look at the path space from x and y, that's the one that we're going to kill. So that's the one we're turning into a contractible space. So what we're making sure is that there aren't any interesting higher homotopies, paths. So this turns out to be connected, the type of connected components. Well, path connected, right? So always path. Path connectedness. So this you would then rightfully write as pi 0 of A. Because in homotopy type theory, pi 0 of A would be the set of path connected components of A. This goes on, for instance, so just sort of as a preview, you could say something like this. So suppose we have A in A, so pointed space, pointed type, so with a selected point A. Then we can define the loop space at A. What is the loop space at A? It's going to be the identity type, just maps from A to A, path from A to A. That's the loop space. It's a space. It need not be it doesn't have an algebraic structure. It's going to look like a group, but when you look at the group laws, they're not propositions. They are further structured. They have interesting homotopy. The loop space can be very, very complicated. How do you get from the loop space to the fundamental group? You kill something. What is it that you kill? You kill the higher homotopies. So the fundamental group is going to be the set truncation of the loop space. It's the components, it's the connectedness components of the loop space. That's one way to think of the if you think of the fundamental group. One way to think of the fundamental group is that what is its carrier set? It's the components of the loop space is the carrier set. So now we have a way of making a fundamental group. So that's why truncations are so important, because they give us a lot. So you see, they gave us logic, and they gave us an inroad to homotopy theory.
The one truncation is the fundamental group point.
The one truncation of, like if I just say, oh yeah, okay, so the thing that you would call this, right? This would be the fundamental groupoid. But you should first find a book which defines the fundamental groupoid in classical topology and then compare to what you get here. But yes, that's exactly what's going to happen. And I think they really want to get in, so we're going to finish.